Throughout the class, we are going to talk about a few more measurements. One of the measurements that we'll talk about is has to do with concentration. So concentration is just the number or mass of particles of a substance contained in a specific volume. And so, one of the things that we will talk about, or that you'll hear a lot, is that you'll have a solute in a solvent, right? And so the solute, a lot of times here, is what we would talk about as the particles, right? And then the solvent is that specific volume. In reality, when we talk about this, you can have a solute that can be a solid, liquid, or gas. So the solute can be a solid, a liquid, or a gas, and the solvent can be a solid, liquid, or a gas. And there's some different terms that we use to describe this, but a really good way to identify the solute versus the solvent is there's just less of it. That's it, right? So there's less solute in a solvent. So if we look up here, these little pink dots, that would be the solute. It's dissolved in the solvent. That's the blue water. This would be a high concentration. There's lots of solute. This is a low concentration. There's not very many of those particles. This is just really frequently used to, concentration is just really frequently used to represent mixtures of different substances. Some other examples of this are concentration of oxygen in air, or pollen count, or the proper dose of an antibiotic. So we run into this quite frequently. Another measurement that we'll run into is density. Density is just the ratio of mass to volume. So when we talk about density, we represent density with a D, and we solve for density by taking the mass and dividing by the volume. A lot of times we will represent mass with an M and volume with a V. This is an extensive property. We talked about that in one of our previous screencasts. A lot of times it's used to characterize a substance because each substance has a unique density. Units for density include grams per milliliter, grams per centimeter cubed, because 1 milliliter equals a centimeter cubed, or grams per cc. You'll also see every so often grams per liter. We have a layered column here. The reason this is a layered column where these have separated out is because they have different densities. When we talk about density and this particular formula, I really like to use the density triangle to help me remember it, where mass divided by volume is density. In this, you cover up or you circle the one unit that you're looking for, and then the arrangement of these can help you figure out what to solve. So if you're moving up to down, you're going to divide, and if you're moving across, you're going to multiply. So let's do a density example where we use the density triangle. A lotion's density determines how easily it can be applied and spread on the skin. A lotion that's too thick, that means it has a really high density, can be difficult to spread and leave a really greasy residue, while one that's too thin, a very low density lotion, might not provide enough coverage or moisture. You've made a lotion from a new recipe. A 150 milliliter sample weighs 136.5 grams. What's the density of your lotion? So if we look at the density triangle here, where we take the mass, divide by volume, that gives us the density. What we are solving for here, what we're asked for, is the density. So this triangle can help us. We can take the mass and divide by the volume to get the density. So I'm going to take 136.5 grams and divide by 150 milliliters. Now, when I put this into the calculator, I get 0.91 grams per milliliter. Let's do a significant figure check. This has 4 significant figures. This has 4 significant figures, but this only has 2 significant figures. If you run into a problem like that, where you need more significant figures, you can just add them on after your last non-zero digit. So this would now be 0.9100 grams per milliliter. So let's do another example. Let's say that we are asked to calculate the volume in milliliters of a liquid that has a density of 1.20 grams per milliliter and a mass of 5 grams. When we look at the density triangle, where we take the mass divided by the volume equals the density, we are solving here for volume. So we're calculating the volume. That's what it's asking us to do, right? And so when we look at this, it has a density equal to 1.20 grams per milliliter and a mass equal to 5 grams. And then, of course, we're solving for the volume. So if I use the density triangle, I can take the mass and divide by the density, and that should give me the volume. So I'm going to take 5 grams. I'm going to divide by the density, which is 1.20 grams per milliliter. And when I do that and put that in my calculator, I get 4.1666 repeating. When you look at these units, you have a gram in the numerator and a gram in the denominator. Those cancel. Now the milliliters are in the denominator of a denominator. When that happens, it's going to flip back up to the numerator. And so that's how we're going to get the milliliters there. Let's do a significant figure check. We have 3 significant figures here. We have 3 significant figures here. So we need 3 significant figures in our answer. Those are going to be the numbers that we're going to use. We're going to look at that number for rounding. So we should get 4.17 milliliters as our answer. Now, all the way through this, we've done some math. And so one of the questions that you may be asking yourself is, well, how do we know if a value is right? Or how do we know if a value is correct? And so chemists use accuracy, precision, and then ultimately percent error to help us figure this out. So when we talk about accuracy in science, we are just talking about the agreement between a measured value and an accepted value. When we talk about precision, this is an agreement between repeated measures. So let's look at the dartboard down here. If you are throwing darts at a dartboard and you get one kind of way over here, here, and here, they're very far away from the bullseye, so their accuracy is not very good. And then those 3 darts are not close together, so the precision's pretty bad too. So this would be an example of not very good precision and not very good accuracy, so low precision and accuracy. Here, we've got 3 darts that are clustered here. They have really high precision. They've got really great precision. Those 3 are close to each other. So those, if they were measurements, those 3 measurements would be close to each other. But they're really far away from this bullseye here. So the accuracy is not very good. Here, these are close to the bullseye, so their accuracy is better, but they're not close to each other, so the precision is not very good. And then here's an example where we've got high accuracy and high precision. Those 3 are right on the bullseye, and they're very close together. Now, one of the ways that we can measure this mathematically is using percent error. And so to calculate percent error, to tell us how our percent error will tell us about the accuracy of our measurement. We take the experimental value and subtract the accepted value, or the known value, and divide by the accepted value. Now, this is the absolute value, so we're not going to get a negative, and then we're going to multiply it by 100. The lower the percent error, the better the accuracy. So let's look at an example, and we're going to refer back to that lotion that we made. So you figured out the density of your lotion, and you have this lotion, and that published recipe, they said, hey, look, that density should actually be 1 gram per milliliter. Well, you measured your density and you figured out it was 0.910 grams per milliliter. What's your percent error? So this right here is our experimental value. And this is our accepted value or our known value. Right? So if you look back at the previous equation, you can see that we're going to take our experimental value and subtract that accepted value, and then divide by the accepted value. And this is the absolute value times 100. Okay, and the lower that percent error, the better that, the closer you are to the right value or the known value or that accepted value. So we're going to fill in our numbers. We're going to take 0.910 grams per milliliter. We're going to subtract 1 gram per milliliter. We're going to divide by 1 gram per milliliter and multiply by 100. When we do this, we get 9%. When I look at 9%, in general, as a scientist, we always try to keep our percent error at 5% or below. So 9% is particularly high. When we look at this, the density of water is about 1 gram per milliliter, and this is less than that. And so to get this amount up, my guess is that when this lotion was being made, not enough water was added. So we can use things like percent error to evaluate our products that we make, and then come up with ways in which to fix some of the problems that we have. This ends for us Module 1. We will do some of these problems in class, and then we will go on to Module 2.